Okay, so today we're going to be talking about conversions, scientific notation, and significant figures. So this is kind of like where you're all saying, I love math. Um, Anyways, I know most of you aren't saying that, but we're going to do it anyways. So, first thing I'm going to start off with is something super important for not just chemistry, but you'll use it in mathematics, physics, any sort of engineering, um, and any sort of science, really, is scientific notation. So, what exactly is this? Well, scientific notation is any number written with a specific set of rules. It has two parts. So, I'm going to write those down first and then I'll explain it. So, number written in scientific notation has two parts. I'm just going to write side note, but definition's right there. So our first part is going to be a decimal. It's got a decimal, not a whatever that was. And the second part is exponential. So it's got a few rules that you follow. So with the decimal portion, I'm going to write it again here. Probably would have made more sense to do it that way, but whatever. So with the decimal portion, you have a number between 1 and 10, but it's always less than 10, not less than or equal, less than. And then for the exponential part, it's 10 to the power of n. So what that looks like is this. So it's times 10 to the power of n. So the value depends on how many times the decimal point is moved. I'm going to write that in blue. Estimated that pretty badly. Let me fix that. Okay, so I'm going to give you an example real quick. So we have the number 10,135. So as a number, that's perfectly fine to write it like that. But say you needed a certain amount of significant figures, which we're going to get into later, or what have you. You can express this in a different way. So just because you can't see it doesn't mean it's not there. There is a decimal point right there. Because you could write 0.000 times infinity of zeros. Like, it's going to keep going forever. It doesn't matter. But the fact is there is a decimal point there. So this is kind of how you can tell what your n value is going to be. I'm going to give you another example with the opposite direction. But because we're moving to the left, we go 1, 2, 3, 4. So we move to the left 4 times. 1 is definitely a number between 1 and 10, so 1.0135. 1.0135. I'm going to write down what it is. It's between 1 and 10. And it's less than 10. So that checks out good. And we have to write our exponential part because this does not equal this. It's missing something. So because we move to the left 1, 2, 3 4 times, we're going to write times 10 to the 4. And that's going to be equal to the same thing. So I'm going to pull up a calculator real quick and show you how that works. I'll go into how to use scientific calculators and graphing calculators a little later. I'm going to just type it in manually for right now. But there is a trick to doing this way faster. Alright, so anyways, 1.0135 times 10 to the power of 4 is equal to that number. So that's how we would be able to figure it out. So I'm going to give you one more example. This one's going to be opposite. And then I'm going to draw a little example chart thingy to kind of explain the correlation between moving left or moving right. So I'm going to just make a number up. So let's say we had 0.002312. Alright, so the first thing is we have to get, and then let me write exponential. Exponent is 10 to the 4. Sorry, I'm all over the place. So anyways, we have to somehow get this to be a number between 1 and 10. So how would we do that? Well, here's our decimal point. We're not moving to the left, it's just going to make it smaller. So we have to move it to the right. So 1, 2, 3. 2 is between 1 and 10, and it's less than 10, so let's write that out. So we have 2.312. Now because we're moving to the right, our exponent has to be negative because we're going from a small number to a bigger number. So of course it has to be negative. So let's count how many times we moved. So I'm going to write down our checklist. So 1 between less than 10, and then that's a check. And then our exponent will be to be determined. So if you want to try and figure it out yourself, just pause it and then go, but I'm going to solve it right now. So you have 1, 2, 3. So because we moved it to the right 3 times, we're going to type times 10 to the negative 3. So let's plug that in the calculator and see what happens. I don't know why I closed that, but let me open it again. So we have 0.002312. And then we want to get it over to this. So we have 2.312 times 10 to the power of negative 3. Make sure you use the negative symbol on your calculator. If you use the minus symbol, it's going to either say domain or syntax error or something like that. So anyways, if you can look here and look here, it is the same exact number. So real quick, before I give you the trick on the calculator, so wow, I cannot draw a line today to save my life. So if the decimal moves to the left, then we have positive exponent. If the decimal moves to the right, we have a negative exponent. That's just kind of a little trick to keep you, in line with not having to just type this in your calculator to figure it out. You can do most of these in your head because it's all powers of 10, so you're really not changing any numbers. Alright, so I'm going to write a few examples down, and I want you to pause the video and try to solve these, and then when you're done, I'm going to show you how they're done. I'm going to give you the answers. I'm not really going to go over it because we did 2 examples already. But let me write these down. Alright, so we have 0, 432, 315. Alright, I got 3 more for you. So we have 152. And 2.24. So I want you to either convert them to scientific notation form, or convert them back to regular notation if they are already in scientific notation. Pause the video and work on these. Alright, so I'm going to go ahead and solve these underneath in red. So this one's moving to the right. I'm going to go 1, 2, 3, 4. We have 4.32 times 10 to the negative 4. Alright, this one is moving to the left. So we would have 3.15 times 10 to the 2. This one's moving to the right. 1, 2, 3, 4, 5. So we have 4.18 times 10 to the negative 5. This one is moving from the right to the left. So you have 1, 2, 3, 4. So you have 7.0152 times 10 to the 4. So this one, all you have to do is you do 1, 2, 3, 4, 5. So it should be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that should be your answer. And then this one should be let me just double check, make sure I didn't miss anything. 1, 2, 3, 4, 5, 6. Okay, that's right. Alright, so that's pretty much scientific notation in a nutshell. It's super useful when you're doing large calculations that have huge exponents, because you can use the exponent rule when you're doing division or multiplication, since most of the stuff is going to be in scientific notation. It makes doing a lot of these big calculations in your head like super quick. Alright, so next thing we're going to go over is rules for significant figures. So let me go to a new page. So we have significant figures. So you're probably thinking, what is that? Because I know when I first took chemistry, I had never heard of this before, and I was super, super confused. But I'm going to give you guys some really foolproof rules so that you know how to tell when something is significant. Alright, so rules. Oh, and just so you know, significant figures are not the end-all be-all of everything. They just kind of help with getting rid of rounding errors. And keeping everything standardized in calculations, because there's a set of rules that people follow as opposed to just guessing where you're supposed to round. So anyways, 1. I'm going to write it down. Digits from 1 to 9 are always significant. Okay, so an example would be like you have 143. All 3 of those are between 1 and 9. So right there, you have 3 sig figs. That's like the shorthand way of writing it, because nobody wants to write significant figures over and over. So rule 2, combine zeros. That means it's like you have a number sandwich with a 0 in the middle. So combine zeros located between non-zeros, always significant. Okay, so let's do an example of this. Something easy. 103. So you have a 1 and a 3, so those are non-zeros, and the 0 is in between it. So right there, that would be 3 sig figs. I realize that is a different color. I'll change this one to be the same. Okay. Alright, so this is where you're gonna probably get a little confused when you start doing these. You have leading zeros. When you start getting the leading and trailing zeros and all that, it gets a little bit confusing sometimes, but it's not too bad. So a leading zero is something at the beginning. So at the start of a number used to indicate the position of a decimal point. They're never significant. Let me just write it down here. Never significant. So an example of that would be like 0.00322. So if you count, you have a total of 1, 2, 3, 4, 5, 6 numbers, but you only have 3 significant figures. So the reason for this is because if you remember back to about 10 minutes ago, when we were doing scientific notation, all you're doing is moving the decimal point. So this would be 1, 2, 3. You would have 3.22 times 10 to the negative 3. That's why those zeros are not significant, is because you can just write it in scientific notation and they're gone. They're still there technically, but they're not there in the sense that you're looking at them as you've written down the number. Okay, so our last rule, this shouldn't be our last rule. Should have one more. Yeah. Okay, so you have number 4 is trailing zeros. Well, this is like 2 parts. That's why I was thinking there's 2 rules left. My bad. So trailing zeros. At the end of a number, they are significant only if there's an explicit decimal point. So it's significant only if there is an explicit decimal point. So what that means is you have, I'm going to write the same number, well, not the same, but the same 3 numbers. So you have 100, 100 with a point, and 1.00. So in this one, these are trailing zeros, so we only have 1 sig fig. But in this instance, there's an explicit decimal point, so we have 3 significant figures. Right here, this is also an explicit decimal point, so you have 3 sig figs. And then that would kind of be how you do all these. They're not really too challenging or anything. It's just you got to remember the rules. So I would say just writing them down. and just try to remember them as best as you can. I know it's a lot, but it gets easier the longer you've done this. So I'm going to give you some examples, and then you can work on them and pause the video, and I will answer them at the end. Okay, so 1, 2, so we have 0.0010200. We have 1.100 times 10 to the negative 3. 700 and okay, so pause the video, work on these, and then I'm going to answer them. Okay, so let's work these out. Apparently I've run out of room, so I can't scroll down. I'm going to move this up a little bit so I have room to explain stuff. So for the first one, these are leading zeros. They don't count. But there is an explicit decimal point, and these are trailing, so they would count. So you have a total of 1, 2, 3, 4, 5. Okay, so for this one, this would be the same thing. So you would have 1, 2, 3, 4. You would have 4 significant figures. So for this one, this was kind of a tricky one, or a trick question almost. There's no decimal point there, so you only have 1. And then this one, there's an explicit decimal point, so you have 1, 2, 3, 4. And then that would be how you do these. They're not too challenging. You just have to pay attention to the rules. If you have any questions, please ask.